Great. In this session, we want to now look at another importance of dimensional analysis, which is using dimensional analysis to find the identity of a symbol in a particular equation. So when you are given a particular equation, it is possible for you to actually know what a particular symbol inside the equation stands for, right? So it means that the other components that are not needed, right? That are not and that are so the other components are known in the equation. That's the thing. So the other components are known in the equation, and some of them we don't know what they stand for. So you can use dimension analysis to know what those ones stand for. So we are going to use few examples again, and then solve them. So I told you always, right? These questions are taken from the attack. So if you're having your attack, you can these questions you can easily relate to these questions, and then we look at how to solve them, and then we take our time in explaining them for you, right? So you can follow along by using that. Yes. So let's look at this example. Yeah, this is an example from Atake, as I said. So let's try to find what the symbol they are looking for, what the symbol A stand for in this equation, and what the U stand for in this particular equation. But they told us that S is distance. So they say S is distance, and then T is time. T is equal to time. This is what they told us. But we don't know what A is, and we don't know what U is. Right? I want you to look at something. You realize that in each of them, how many terms are there? Right? On the right side, we have the S as one term on its own. And then, sorry, that was on the left side. So on the right side here, we have UT as one term, and then this one too as another term. We also told you how to understand or where to go and understand what terms are, right? So now I hope that by now you know what a term in a particular equation is. So yes, this is a term and this is another term. So there are two terms here. So that in each term, aside the first one, the one on the right side, you see that they are looking for these guys, U, and then they are looking for what A also stand for, right? And so it means that in each term there is at least one item that is not known. So there's no one item not known here, and there's one item not known here in this term. So now, in the following the previous session, we saw that for equation to be valid, what should happen? The terms, right? Each term should be all the terms must be equal to each other. All the terms must be equal to each other. So we are assuming that this particular equation is already valid. So the terms must be equal to each other dimensionally. By dimension, they should all be equal dimensionally, right? So we know S, but we know this particular term fully. We know the S term fully. We know the UT term, we don't know it fully. The half 80 square, we also don't know it fully. So what you have to do is that you have to compare the term that you know their dimensions fully to the ones that are not uh, known fully. So you cannot use this term to equate to this term. You can't, because there is one unknown here, which is the U, and there is one unknown here, which is the A. So it's practically impossible to compare them. But then if you look at the S term, we know the S term fully. There's no unknown there. So since we know some that this one we know it fully, we can use this one that we know fully and compare with those that we don't know fully. So I'm going to first fetch the dimensional expression of the term on the right side, which is S. S is distance, right? So I'm going to use this L. So L is equation one. But the second one is UT. So now the second one is UT, right? This is the same as expression of U times the expression of T. But then we don't know what U is now. So we are going to keep the U in its bracket because we don't know the expression. But then the T, we know the dimensional expression of a T. They say T is time. So since they say it is time, they have defined it for us. We know can convert, we know it, so we can convert it to its dimensional expression, which is T, right? So this is equation two, right? Now we said dimensionally correct. So that means that the term S should be equal to the term two. Term one should be equal to term two. If term one is equal to term two, it means that the expression S should be equal to the expression UT. And then the expression S, we got that the dimensionally it is L. But for the UT, what we got, like the U, we don't know it, so we keep it like this. but we know the t. This is what we got. Now, if you move this thing here, we are going to see that we have we have to make u the subject. So we're going to L is equal to dimensional expression of u times the expression of t. I will divide both side by t, both side by t, right? This one will simplify this. Then you have um let me write it like this. Let me move up here for you. So then what we have, you have L over T is equal to only U. And then this one can be written as L T to the power negative 1. So the T can become negative 1 is equal to expression of U. The best way of simplifying and simply writing this is to writing L U is equal to L to the power negative 1. So the question says we should find the dimension of U. The question says we should find the dimension of U. So this is it. We have finally gotten the dimension of u. From here, if you know the dimension of u, you can go back to the previous session where we talk about how to use from the dimensional value, you can get the units, right? So the units will now be meter per second, meter per second, depending on what the question tells you, right? Yeah, this is what we get for this particular example. Let's look at another example again. Yeah, so we have this example, and they say v is velocity. V is velocity. We don't know E, we don't know E, we don't know G. G there, we don't know G as well. But we know T, they say T is time. So T is time, T is equal to time. And we don't know H as well. We don't know K. We don't know K, but they say A is acceleration. That's what the question says that we should focus on. A is acceleration, right? Um, so now let's break the things down. So we know v is a velocity. If v is velocity, so this term is fully known, right? This one is if we don't even know this term. And in this particular term, we don't know everything because we know t plus g is there. T plus g is there. So we don't know g in this term. But if you come here, we also don't know this one fully. So all the ones on the right side are not fully known, but the only fully known is the v is velocity. So we are going to find the dimension of v, right? Which is equal to lt to the power negative 1 because they say it is velocity. If it is then known like that, then we can focus on e. Then the dimension of E should be equal to the dimension of V because that's the rule, right? If you are able to add them or compare them, then they are dimensionally, each term is dimensionally the same, or the terms are the same dimensionally. So now if you do that, so the dimension of E will also be like LT to the power negative 1. So we know E already. So we know E. Now let's focus on G first. They say T, they say dimension of T, right? is is a time, so it's t. But then you see that at the top we are doing t plus g at the top there. So we are adding two things. Whenever you are adding two things and you know the dimension of one, right? The second one should also, the second term should also have the same dimension. You can only add two things, right? Or compare two things when they are dimensionally the same. So if the dimension of t is time and we are adding or subtracting anything from it, then the other thing that we are subtracting or adding to it should also have the same dimension as what we know. So t plus g, we know t is time. So if t is time, then the g that we are going to add to it should also have the same dimension. So g is equal to the dimension of t. It should have the same dimension as t, then it's also time. So g simply is also having the dimension of time. Now let's continue. So we know E already and we know G also. Let's continue and talk about the H. Also now for the H, we are going to take this entire term and compare it to the term V. And we know that dimension of V should be equal to the dimension of T plus G all over H, right? At the top. But we know the dimension of T is what? Capital T plus the dimension of G, we calculated it already, is also T all over. The dimension of H is what we don't know. So we keep it in this bracket, right? Square bracket. But we know the dimension of V already. So this one become LT to the power negative 1, right? Because that is our V will be equal to, the top become 2t, right? 2t over the dimension of h. Okay, so if you do that, we are going to make h the subject. So dimension of h will be equal to 2t all over LT to the power negative 1. So if I do that, I'm going to have 2t squared over L. So at the end of the day, the number, if you are talking of dimension, the number doesn't count, become t squared over L. So this is h. The dimension of h, right, is over L. Yes, yes. So this is what we have at the end of the day. Now, we are looking for a, right? And now v, we are going to compare the v to the last term, which is ak, and we know the dimension of. So let me compare. Do it like this, and the dimension of a is acceleration. That's what they said. So it's going to be like lt to the power negative 2k, because we don't know that of k. So if you make k the subject, we are going to have the dimension of v over the dimension of a. So you finally have k is going to be, dimension of v is lt to the power negative 1, and the dimension of this is going to lt to the power negative 2. This one will simplify this one will simplify this. At the end of the day, you have t as your value. So k is simply t, our h is t squared over L, and then our g is t, and e is also lt to the power negative 1. Let's look at a last example. Yeah, this particular one. So I will give you a clue for you to try it on your own, right? So the one that we fully known is force. This is a force. This is mass. This is V. So we don't know V. In this section, we don't know V, right? Then, but we know R. They say R is the distance or radius, so it's distance. And then we also don't know I. So what I want you to focus on is to find me the dimension of V and then the dimension of I. Yes, so then T is time. So T is also time. Take time to go through and then see if you can find the dimension of V and dimension of I in this particular expression. And remember, let me give you a last clue. The dimensional expression of force, right? MLT to the power negative 2. And for R is distance, right? Dimension of R is going to be L. And then the dimension of time is going to be T. And the dimension of mass is going to be capital M. So you use this to actually solve for the V and the I. Then we are able